So as it is inside, my name is Lionel in French. Lionel Renault. I work for Hydro-Québec, which is the power company, power utility of the province of Quebec in Canada. And I work for the Research Institute, so we are developing many projects to help our workers to be more efficient or to help increase cable life or accessories life, lifetime, etc. So I'm going to present you a project we started many years ago, 6 or 7 years, and it's about measuring partial discharges within accessories. I'm going to explain everything. And it is done for safety reasons, mainly, because as we are going to see, it's really important to keep the workers safe when they are working. So during this presentation, and just a little note for those who were thinking that they were becoming a testing for wireless medical devices, it's a little mistake in the map here. So I hope for those who would have thought that they will enjoy the show. And so during this presentation, I'm going to introduce PD measurement, PD for partial discharge. We are going to see what are the impacts for safety and the principle of the PD detection. Then I will go for the system overview and talking a little bit of hardware, but not too much, and more software. And about software, it's really difficult to show, diagrams or everything. It's difficult because the presentation is short and we can see much more on screens. So I will talk more about like programming philosophy, what we did, what decision we made, what choices we made. So first, what is an underground vault? And what are components? Well, vaults are like manholes or transformer vaults. We find them next to the streets many of the time. There are holes where workers can go, and in those holes, you have cables with joints, or you have instruments, transformers, interrupters, and connectors, fuses, etc. So that's the area where the workers are working. So if we take a straight joint, the same as you can see here, for example, in the photograph, if we take a straight joint, what is a partial discharge? Well, it's like a mini breakdown. A breakdown caused by the electric field, in fact, and caused by a malfunction in the accessory or something bad, like a poor contact, a bad electric path, a damaged cable when it was installed with the joint, or a cavity in the insulation. All those conditions can lead to a breakdown, a partial discharge. And the problem of this partial discharge is that it's a clue. How do you say? An indice? Tell me, Jean-Claude. A clue to it's prior to a failure. So we want to detect it before it's becoming dangerous, because it can explode. Why it can explode? Because all those accessories are made of plastic and polymers and everything, and when there is the breakdown inside, it burns and it releases some gases inside the vault. And as it is closed, if there is an ignition, it can cause an explosion. So if there is a worker inside at the same time, it's not good for him and not good for the company and everything. So what we want is do preventive maintenance and remove those defective components before any accident. And the PD sniffer, as we call it, it's a stick, a probe. We are going to see a little image. The PD sniffer helps this worker to detect PDs, and then he can go out and raise an alarm. It has to be a quick diagnosis, highly reliable, difficult word, safe mode, 100% certainty. That means that we want to be sure that if we say there is no PD, there is no PD. We can be wrong if we say that there's one, but we can't be wrong if we say that there's no PD. So it's all the, how can I say? All is made to to have a safe mode, but we don't want to raise too much false alarms either. So that's why it's a long development, because it's a lot of signal analysis and conditions and etc. So to go on, the principle of detection. When you have a partial discharge, as you can see, there's a partial discharge here just on the left of the joint. Okay, and, oh, sorry. When there is a partial discharge, there is a current going, because there is a signal created, going on each side of the breakdown. So this current creates a magnetic field that can be captured by an antenna. That's the main principle. See, if you see on this diagram, and the PD is outside of the joint, what happens is that we have two sensors on each side of the joint. So the two sensors see the signal with the same polarity because it reached them on the same side. If the PD is inside, what will happen is that the signals are going to be inverse polarities. So it seems simple like that. That's the theory. It works. But behind that, we have a lot of signal treatment and etc. But that's the main principle. Our system is made first of a worker. We still need him or her. And you have the probe here, which is the sniffer. You see one probe, but in fact, there is another probe that can be connected to the main one to make these two probe measurements. So here, the probe, a cable, a computer, a local database. So, so that's the main overview of our system. And we call it a mobile team. I call it here mobile team because everything is in a track. The team is made of two persons, and only the probe goes inside the vault, and the computer stays in the track. And the probe has many LEDs to raise alarms or say it's safe. Okay, so the mobile team here, it's simple. There is a PD, it's detected, and it goes all along the cable. It's acquired by a data acquisition card, high-speed digitizer, analyzed, and it gives a result. And everything is stored on a local database. I will talk about that later in the presentation. For the hardware, not too much time on that I will spend, but it's mainly done with, you have an antenna here just for the phase tracking for the 60 Hertz, because we need to know where in the cycle the partial discharge happened. It's common in this kind of measurement because some partial discharge can be analyzed particularly because where they happen in the cycle. And there is the antenna for the probe, as we see earlier. And there could be another one if we have two probes. So we have many filters available, and it's all it's a own-made electronic board, this controller. And we have two channels. So this is an acquisition card we bought on the market, and you will see just the next slide. And everything is recorded. So if we want one sensor, we use the two channels with different scales, so it's quicker. And if we have two probes, we use the two channels independently for each sensor. So the high-speed digitizer we started to use many years ago was an Accurus one. It became Agilent, and it was very perfect for our needs because it's a high bandwidth, 1 gigahertz. It's also 1 gigahertz sample per second. It's quite big and quite quick, and it can take acquisition by segments. So you don't need to trigger each time. It takes segments because it's about 200 microseconds, our data acquisition time for each segment of data. And you see that, 50 millivolts to 5 volts input ranges. Now, we could have used maybe the 5154 from National Instrument. Personally, and it's not because it's NI weak, but I always prefer NI instrumentation because it's easier to program. And on all the drivers of Agilent of all the manufacturers are not always good, and you have to rewrite them most of the time. So we could use this board. The only difference is maybe the smaller scale, the 100 millivolts for the NI and 50 millivolts for the Agilent. And as we detect PDs smaller as 10 millivolts, it could be an issue maybe because of the noise and everything. We have less resolution than 100 millivolts, and but I wanted to show you that it would be possible to have a National Instrument board. For the software, well, that's all the question of philosophy now. What we did, we started this project, and we knew that it was a long-run project on several years because it has a lot of impact. It has to be tested by doing pilot projects in the network with workers to be sure it works, analyze hundreds and thousands of signals. So we wanted to be able to develop something from the prototype to the final version, but being really flexible. So at the end, the final version would have been the evolution of the prototype, but would stay a nice and clean software. So we tried first to design our old data structure. So from the bottom to the top, our data structure is made of the database, Microsoft SQL Server. I just look at the time because, okay, it's all right. So the database, Microsoft SQL Server, everything is stored on that. Data, configuration, everything. On the top of that, we have the database connectivity toolkit of LabView to be able to communicate with our data structure, which is made of classes, oriented object classes. And I will talk about that also why. On the top of that, you have the VIs we developed to read our classes, and the data is then either showed to the user or the user can enter some information. So those are the layers. The fact is we want to avoid database changes. When it's done, the architecture, we want it to stay like it is. Why? Because lower, in fact, deeper is the data change and higher is the development impact on all the other layers on top. So we prefer just to have maybe change the data structure in LabView classes, that's all. That was our philosophy. And as nowadays, if you go on Wikipedia or internet, you can type that, and you will see that people say that now both oriented object programming and database management systems are quite common in software. So we are able to make classes as close as possible to the database architecture. That's the other advantage we wanted, and to be really flexible with data. We use classes for that. We take advantage of the data abstraction and the encapsulation of data, but we didn't, in fact, made oriented object software because we don't use inheritance, for example. So it's just the question of data representation. To be efficient and flexible during development time, we then thought that we wanted to be able to add or remove a parameter anytime during the development. Parameter, I mean, for example, I want to add a new parameter value for a new filter or a new length of something we added in our system. But we wanted to be able to do it dynamically, almost dynamically, or with less impact as possible on the software. So what we did with the classes, we defined first a class to indicate what is the parameter ID and what is the version of the parameter. But in this class, there is no value of the parameter. The value of the parameter is in another class here, and it's linked by its parameter ID. And then each parameter is linked to a topic. And each topic can have a phasor. What that means is, for example, here I have a topic ID, the general topic, and I have several parameters, length, number of groups, filter values, etc. And this topic itself has a phasor analysis parameters, which is just on the top of the tree. The separation of the parameter version and the value is really great because it allows us from prototype to development to test different sets of configuration. And we can go back to a previous set of parameters with a previous version quite easy by accessing the database and reloading the parameters. And also, during development and at the end, close to the deployment, it's really practical because we can have a deployment version, which is maybe more stable, and keeping development version where we can just adjust some parameters based on our pilot results, pilot project. Am I clear or not? Yeah, good. Because I'm not sure to be so much clear sometimes. So if you see our mobile team, it's quite static now, so it's going to move. Well, no, to shrink, in fact. But we have several mobile teams, in fact, several trucks all over the province. So they're working together in sometimes the same unit, Montreal or in the eastern of Quebec, etc. But at the end, they all have a local database in their truck, and what they do with it? Well, we want them to save all their data on the centralized database. So everything is synchronized. They can save their result, and they can upload new parameters. Why new parameters? Because of all the structure we made. We have an administrator profile, and the administrator has the ability and has the rights to add or remove parameters in the database. And we have some analysts, people who are watching the results, that can set new parameter values for those parameters which are added or not. So this is the entire system from the worker to the administrator through the analysts that are watching all that. The parameters in LabView, we did it as a tree representation. Because the tree representation is very practical. It can be dynamic. So as soon as we load the software, the trees is implemented, the tree are, or the tree is here, implemented with the data coming from the database, and as it is dynamic, it is created. And the administrator, by going into that tree, in that interface, has the rights to add a new parameter, but with a different, it's all in French, but with different values for this, well, properties for this parameter. But that's the analyst. So we see that the administrator can add or remove a parameter, but that's the analyst in another view that has the ability, the rights to change the value. That's how it does. It is done. Now, data synchronization. We made it asynchronous. That means that the workers can do that once a week, once a month. It's as soon as they're plugged on the network. And as the trucks are in garages and etc., there is not always the network there, so they have to move the truck next to a plug, and they do it. For sure, in the future, maybe we will do it wireless or something like that, but it's very difficult in that kind of company like Hydro-Quebec or major companies. It's a question of security, data security, so for now, it's like that. LabView data is converted is put in XML files format to be transferred to the database. Why? Because it's so simple. All the tools are existing, in the SQL server to bring directly an XML file to a database. So great. The only disadvantage is we can't put strings bigger than 2 gigabytes. But for our needs, it's not a problem. My conclusion now. we made thousands, and I say really thousands of measurements. And out of maybe this 100 and 1,000, because it was a month ago, this number, and out of that, maybe the first 2,000, we looked at each signal, analyzed it to be sure that we were right, taking the good decision, etc. And it worked now. The performances meet the expectation. And our philosophy of development led to that. The fact that we decided to be flexible, to use an oriented object and database, and etc. That's what I'm saying on the second point here. I won't repeat it. And at the end, the other big advantage. But now I tell you it becomes a disadvantage. But the big advantage of the database is that for data mining, it's really, really nice. You can, after 1, 2 years, 3 years, you can have a look back at what you did, all the cases you had, where the problems come from most of the time. Some vaults are really more exposed to problems than others, and we can see that. The problem of that now, it's the system is so big that it's really difficult to maintain, because we have a lot of databases in each, each track has one, we synchronize. So as soon as there is a problem on the computer, we have to go and repair it and maintain, so you have to have specific persons to do it. I will dream now that it's working, I would dream of a same system without any database and just alarm red or green. But we had a lot of fun. So thank you very much, and if you have any question, I'm ready to answer them. Yes? Excuse me, my phone is perfect time. Okay. Go. What about elbows and sprint cones and stuff like that? Okay, if I understand, you're asking me what about elbows or other type of connectors, yeah, that are not straight. Yeah. In each, for each accessory on the network, you have always a current path anyway. So even if it's like an elbow, it doesn't matter. We put one sensor at the beginning and the other sensor at the other part, and it works. The problems are more with like multiple branches joints, H joints, I don't know how you call them, but when you have 4 branch or 3, in that case, what we do is we do multiple measurements, and maybe, and we try to see if there is a PD within the accessory, and if there is an alarm, there's still a chance that it's not within this accessory, but we have other, I didn't tell you that we have an expert team. This expert team, once an alarm is raised by the sniffer, goes and check that, validate the signal, so we validate after that. But we can do measurements on anything. Any other question? Yes? About the signal treatment? Okay. So the question, if I understand it, is what did we do for the signal treatment and everything? That's interesting because that's a part of the presentation I don't talk about because it was too short. But in fact, the main principle in that presentation is the time clustering in that software. That's why the last slide, I'm so wise. Look, oh, sorry. In the last slide, I show you that you see this cluster. This is a cycle. In each point is a signal we acquired during the test. The test lasts about 20 or 30 seconds. So by analyzing the signals, the shape factor, the frequency of the signal, the number of peaks, etc., we can have an idea if it's a PD or not. But if we do that calculation on each signal, hundreds of signals, it's really long. So this is classic clustering. Classic clustering is you take some characteristic of a signal, of many signals, and based on those characteristics, you group signals because you think they are the same. Time clustering is we first group all those signals based on their time shape, only the time shape. And we put at the same scale as all the signals. So once it's done, we have an average signal So this is those two are the two average signals of the two sensors of all this cluster. So we reduce noise. We don't have any noise now because of the average of the time clustering. And now we can calculate many parameters characteristic of these signals, but just once for one cluster. So here we have one, and this is the opposite cluster. Much of the time when you have a partial discharge, you have the opposite on the other part of the cycle, negative part of the cycle. So you have here the partial discharge. It's opposite in the negative part, and you see all the clusters here. So we have 4 clusters to analyze, so 8 signals, in fact, and we just want to watch if those signals are PD or not, and we raise an alarm if it is a PD. And based on the shape of the cluster, we can also say sometimes where it comes from. For the interrupters, the cluster is always flat. And because it's internal discharge within the interrupters that are not problematic. So based on that analysis, we don't raise an alarm. So does it answer a little bit to your question or not? Yeah, it's a very complex algorithm, and I think it's a way to be brevet, Jean-Claude?
It's basically IP and is patented.
Yeah, patented. It's on a way to, I think there is a patent on that now, but I'm not really sure, because it's a huge company and you don't follow all the, all the files. And what we do, it's once a signal is acquired, do I have time to answer 2 minutes?
Yeah. Yeah.
Or is
I'd say, yeah.
Once okay. Once it's acquired, the signal is compared to previously treated signals that were put in a group. So we watch, for example, we had already defined that there are 2 clusters, and I have a new signal. So I see, is this signal like the first cluster in time shape? No. The second one? No. Oh, so I create a new group. And then it's parallel at the acquisition, this treatment. And I put a maximum number of groups, for example, 10. So if I have a signal and it doesn't fit in any of the 10 groups, I have to create an 11th one. I don't do it. I take the other groups and I say, which group can I maybe group with another group? Because I reached my maximum number of groups. That's all complex, and we do that at 2 different, we do that for each scale, and when it's done for each scale, we do that between scales, to group scales. So it's quite complex, but really fun, and it increases the efficiency drastically. Maybe you don't want to ask any other question because I'm so long to answer, no? No? Do you have any question? Thank you very much.